Okay, in this short video, we're going to talk about potential divider circuits that I just showed you in the previous video, but we're going to add sensors into them. So how do sensors make smart circuits? All right, and these are the circuits that you see around that have lights that automatically turn on, or you have sensors that walk in front and they turn on an alarm. We're going to talk about 3 different types of sensors. Now, these are not written anymore in the Tsokos textbook, but it does appear on exams, so it's important to know these 3 different types of sensors. Okay, so this sensor is an LDR sensor. It's a light sensor. A thermistor is a temperature sensor, and a strain gauge measures movement on parts. Okay, so there's certain parts like airplane wings that you don't want to move too much, and you'll be able to sense if they're moving around too much and causing strain on joints and things like that. So we're going to go through all 3 of these and show how they can be put into a circuit in order to make an alarm. Okay, the first sensor is a light-dependent resistor. That's what LDR means, light-dependent resistor. Okay, and if light is hitting it, all right, so during daylight, if light hits this sensor over here, what's going to happen is the resistance of that component, that sensor, goes down. The resistance of the light-dependent resistor will go down when light hits it. In the dark, the resistance of that component is very, very high. So I can create a potential dividing circuit like this. Go back to the last video to see. If I have that component in here and its resistance changes, the fractional resistance will be different. Okay, so this little circle with an X is a light bulb. Okay, that we see here in the diagram. In the daylight, let's say the resistance of that component is 1 ohm. Okay, that would mean that only 1% of 12 volts would be going to that light bulb. All right, roughly around 1% of 12 volts would be going to that light bulb, which would be not enough to light it up. But at nighttime, what would happen is that resistance would go up to 10,000 ohms. Okay, so then now we would say that greater than 99% of 12 volts would be going to that light bulb. So at nighttime, the bulk of the voltage would be here, and at daytime, the bulk of the voltage would be here due to that equation that I showed you times fractional resistance. Okay, that's for potential dividing circuits. So the greater the fraction on a component, the greater the voltage it's going to have from the potential. Okay, so the way a sensor works is it changes its resistance based on an input. Okay, so this sensor uses light as an input. In the absence of light, the resistance is very high. In the presence of light, the resistance is very low. Okay, and that way we can shuffle the voltage around between components. Okay, and if I put a component in parallel to that resistor, it's going to sense the voltage that's going across it, and because it's in parallel, whatever voltage goes here goes down here on that branch. Okay, next resistor, let's talk about temperature sensors. So thermistors are types of sensors or devices that change their resistance as a result of change in temperature. Okay, and thermistors are usually made of ceramic materials, like I showed you at the top over here. So it has like a ceramic material inside of it, and it's like got like a semiconductor in it. And when temperature changes, all right, these materials are going to change their resistance. Okay, metal oxides and ceramics. And here's a graph showing you how the temperature changes. So as the temperature goes up, the resistance of a thermistor goes down. Okay, so think about what's going to happen at cold temperatures. If I had a voltmeter attached here, what would happen to the voltmeter at cold temperatures? Well, at a very cold temperature, the resistance is a lot higher than that component, so the bulk of the voltage would be here. So I would say that the voltage at cold temperatures would be close to 12 volts. Okay, and at high temperatures, okay, if that resistance goes beyond 60 degrees, okay, the bulk of the voltage will be here, so that voltmeter will show a very small voltage. Okay, so if I wanted to have a cold temperature sensor, okay, instead of a voltmeter, I have an alarm. Let's just put or a light bulb that goes on that tells me that, oh, it's too cold in that room. Then I would put it here. If I want an alarm that shows high temperatures, I would move that light bulb over here. Okay, because at high temperatures, the resistance of the thermistor goes down, and the bulk of the voltage will be here, which will then shuffle it down to here, the same voltage. Okay, so then that voltage would be high enough for it to turn on the light. So at a certain temperature, the light will go on and you'll know that that room is becoming too hot. Okay? That would be on submarines or attached to power generators that we don't want to overheat, or inside of your car. Okay, that when components start to overheat, you get a light that turns on. That's probably the circuit that is doing that. Okay, and the last one is a strain gauge. Oh, first of all, just to show you the symbols for thermistor, this is all in your data booklets. Okay, and that's the symbol for an LDR. It's in your data booklet. Okay, the last one, the strain gauge, this is what you would have attached to components. It could be in an airplane, on airplane wings that move around, and we don't want them to move around too much, because if they move around too much, you'll put a lot of stress on the materials and they'll start to crack. Okay, and then the airplane is going to become compromised. Okay, but you can also have this on buildings and bridges. We often have these components so that engineers can take data from moving parts in buildings and structures to make sure that they haven't moved too much and caused too much strain and weakened the structure. Okay, so what a strain gauge is a very thin wire, very long wire that's kind of coiled up and down on itself. And if I cause that wire to stretch, I'm going to make it longer. And the longer a wire is, the more resistance it has. On the other hand, if I compress that, if I bend it in and compress it, I'll make that wire effectively shorter and I'll lower the resistance. So here is the unstretched strain pattern. It would have a set resistance. If I stretch it, okay, by causing it to flex in that pattern like that, okay, if I stretch it, it's going to become longer, the resistance is going to go up. If I compress it, it becomes shorter and the resistance goes down. So the way to read a strain gauge is to have a voltmeter, okay, some type of sensor that is reading and graphing the voltage. Okay, if that thing isn't moving, the voltage would stay constant over time. If that object is moving up and down, if it's oscillating, the voltage would look like that. Okay, and the voltage here, if it went up, that means that it flexed like that first, then it compressed, then it flexed, then it compressed, then it flexed. Okay, and you might have in your device alarms. Okay, so I might have a threshold over here and a threshold voltage over here that is triggered to an alarm. So if it went up beyond that, an alarm would go off and say, oh, this plane is experiencing way too much turbulence. Okay, that's how that sensor would work. So that sensor is just usually connected to a voltmeter or maybe a light bulb that would flicker if it goes beyond a certain voltage. Okay, and those are just three different types of circuits that use potential dividing circuits. Okay, components that use potential dividing circuits to turn them into smart circuits. So the LDR, the light sensing circuit, the thermistor circuit, which senses temperature, and you need to remember that the resistance goes down as temperature goes up, and the strain gauge,